Alright, so a very good evening to all of you. Now finally I have made a video on perturbation theory for all of you, and this video will definitely help you in understanding perturbation theory in a better way, and in the end you would definitely be able to solve a few questions as well if that is your aim, right? So, and I can assure you that you will definitely develop some kind of interest, or you will at least understand what is being asked, right? What exactly is perturbation theory, what is being asked in the exam if you're particularly interested in solving some questions, and in general you'll understand the whole idea of perturbation theory, right? So what exactly is perturbation theory? Why do we need perturbation theory? Let's first set up a background, right? So perturbation theory is basically, what is perturbation? First of all, perturbation is some kind of disturbance or some kind of displacement, right? Now why do we need perturbation theory? Because it's basically an approximation method, right? So there are two kinds of very widely used approximation methods. One is perturbation theory and the other is variation theorem, right? So in this particular video we are talking about perturbation theory, so I'll focus on that, right? So in Schrodinger equation, the general equation that we use in quantum mechanics, there are only a very few systems for which we can have an exact solution, right? There are very few systems, like for example hydrogen atom, harmonic oscillator, particle in a 1D box, rigid atom, right? Sorry, rigid rotor. So these are some of the very few systems for which we can have an exact solution. For rest of the systems, particularly multi-electron systems, we do not have an exact solution. Now to calculate the exact solution, or to calculate the approximate solution for those kind of systems, see, we need to have some kind of energy for those systems. Now to calculate the exact, not the exact energy, the approximate energy for those systems, we take help of the systems for which we have the exact solutions using the Schrodinger equation, right? Now you might be wondering how, using the simple systems like a hydrogen atom, how can we calculate the energy for multi-electron systems? Well, it involves a lot of complex mathematical tools, a lot of complex mathematical series, which will be beyond the scope for a chemist especially, right? A lot of theoretical physicists and a lot of mathematicians do get involved in all of these series and equations, right? So this is not our you can say not our scope, right? If you are interested, you can definitely go and see how it happens, right? It's quite interesting, to be very honest, but it's a little difficult to comprehend for everyone, right? So anyway, so now what happens is, using these complex mathematical tools, we kind of find the approximate energy for these kind of systems, right? So why can't we exactly, first of all, find the solution? Why do we need perturbation theory or variation theorem? Why can't we find the exact solution for multi-electron systems? Well, the reason is that for a three-body system, or for any system which is three-body or more, we are not able to find the exact solution. The reason is, for example, if I talk about the three-body system which involves two electrons and proton, so using the Born-Oppenheimer approximation, which says that the nucleus is basically because of its heavy size or heavy mass, it's basically fixed in its position with respect to the electron, it barely moves. So using the Born-Oppenheimer approximation, we can predict the energy for a proton, for a nucleus and an electron interaction, but we cannot predict the energy for two electrons. We cannot predict basically the spatial coordinates for the two electrons which are interacting with each other, right? Two electrons will repel each other, and we are not able to predict that what will be the spatial coordinates of the two electrons at the same time, right? So it's very difficult, because of which what is happening is we need to find the approximate method, right? And so we make use of perturbation theory. So it's a small disturbance in the system. If I talk about in general where we can use perturbation theory, so for example, if you have a hydrogen atom, right? And if you see the spectral lines of a hydrogen atom, you will see that the spectral lines kind of deviate from its position. Now that deviation happens because of some kind of electrostatic potential that is being applied on that hydrogen atom. Because of that electrostatic potential, the hydrogen atom interacts with that electrostatic potential, and it leads to some kind of perturbation or some kind of displacement or some kind of disturbance in the energy of the hydrogen atom. So that disturbance we can calculate using the perturbation theory, right? So this is one small example that we can take, right? So let's say there is a molecule which we have, for which we know the exact energy, right? Let us assume, and we apply some kind of electric field. Now because the molecule has some kind of dipole moment associated with it, it will interact with this electric field and will lead to some kind of fluctuations in the energy, or some kind of disturbance in the energy. So that disturbance we can calculate using the help of perturbation theory, and we can finally approximate that due to this electric field what could be the approximate energy of the molecule, for which we had already known the exact energy, right? So I have written down here things for you so that it will take less of time of you also and for me also to explain you, right? So basically we have, this is the basic Schrodinger equation, right? H psi is equal to E psi, and I have written down n over here because it can be applied to n energy states, right? A system can have n energy states, so that's why I've written it can have n different eigenfunctions, right? So for n different eigenfunctions, we can have n different eigenvalues, which I have denoted by En, right? So H psi is equal to E psi. Now if a system is perturbed, its Hamiltonian will change, right? So the Hamiltonian operator basically, or the energy operator, is equal to the this Hamiltonian operator I've written with the power 0, right? This is not power 0, this is h naught. I've written down in brackets particularly to differentiate that this is not power, right? This is not h to the power 0, this is h0, h naught, right? So h naught basically depicts the energy of the unperturbed system, or the energy of the system for which we have the exact solution. That is your h naught, right? And this lambda times h1, what is this? Lambda times h1 is basically the Hamiltonian for the perturbed system. That means for the system for which there is some kind of disturbance. This is what we need to calculate, right? This is what we need to calculate. And what is lambda over here? Lambda is any parameter, right? So for example, I was talking about electrostatic potential and how electrostatic potential, interacts with the hydrogen atom, right? So this electrostatic potential is basically your lambda. If I increase this electrostatic potential, the disturbance will increase, right? Or the perturbation will increase. So this parameter basically defines the perturbation, right? So if this parameter increases or decreases, the perturbation increases or decreases. It can be any parameter, right? Depending on which system we are talking about. If you are talking about electric field, then lambda will be electric field. If you are talking about electrostatic potential, then lambda will be electrostatic potential, right? Okay. So this is lambda to the power, this is the unperturbed system, sorry, this is the perturbed system, and h naught is the unperturbed system for which we have the exact solution, using which we are trying to find the approximate solution of a perturbed system, right? Now we will make use of, like I told you, a lot of mathematical tools. So one important mathematical tool that we'll make use of is Taylor series. So what exactly is Taylor series? That if you have a function which is dependent on some parameter x, then that function can be expanded, and it can be written in this form: f to the power lambda to the power 0, right? Okay, sorry, I've just made a small mistake. You can write down over here lambda. So if f is a function which is dependent on some parameter which is lambda, then you can say that f lambda to the power 0, you can write it down as f lambda to the power 0 plus f prime, or differentiation of the function, lambda to the power 1 plus f double differentiation lambda square upon 2 factorial, and so on and so forth, like f triple dash x cube upon 3 factorial. Like that you can expand this whole term, right? So if I try and expand this wave function psi n, and now this wave function is also a parameter of lambda, right? Because it will also depend on the electric field or the electric potential, whatever the lambda value is. The wave function will also differ. If the Hamiltonian is differing, the lambda value will also change depending on the electric field, right? So the wave function will also change. So wave function is also a parameter of lambda, is also dependent on lambda, and energy is also dependent on lambda. So you can write it down as function as it is, right? Psi n 0, right? Psi n 0 plus psi n 1 lambda to the power 1 plus psi n 2 upon into lambda square, then psi n 3 lambda cube, right? Like that you can write it down, right? So where psi n1 basically means differentiation of this function, right? For once, then differentiation of the function for twice. So psi n twice basically means that. Similarly, energy can be also written in this form: E n naught plus E n to the power 1 lambda to the power 1 plus E n 2 lambda square, right? Now what we are going to do is these three terms, like 1, 2 and 3. These three things we are going to replace in this equation, the original Schrodinger equation. So now if we do that, if we replace it, what we are going to get is, so if we replace Hamiltonian operator by this term, first equation, h naught plus lambda h1. So h naught, which is the unperturbed system plus lambda h1, which is the perturbed system, right? Hamiltonian for the perturbed system, into psi n naught plus lambda psi n1 plus, basically I am expanding it in the Taylor series form. I have expanded psi n in the Taylor series form. Similarly, energy also I have expanded in the Taylor series form, and then again we have lambda over here, so I have expanded the lambda in the Taylor series form, right? Now what we can do is we can try and collect terms which have the same lambda value, right? So first we'll try and collect the terms which have lambda value equal to 0 or lambda naught, basically which are independent of the lambda value. So if you see over here, if you multiply h naught and psi n naught, then these two terms are independent of lambda value, right? And these are the only two terms which will be independent of the lambda value, because if you multiply h naught and lambda psi n1, if you multiply these two terms, then it will basically be dependent on lambda, right? So this multiplication is the only term which will be independent of lambda on the left hand side. So I've written down over here h naught psi n naught, right? And if you come on the right hand side, and on the right hand side, which term is independent of lambda? If you multiply en naught and psi n naught, then this term is independent of lambda. Any other term if you multiply, it will be dependent on lambda. So then over here I have written h naught psi n naught. Since basically the coefficient is same, we can equate both of them. So h naught psi n naught is equal to en naught psi n naught, right? This is very obvious. This is a very obvious thing that came out, that this is the exact solution for a system that we already know, right? So from here we don't get anything. So now what we do, we again collect the next higher term, that is lambda to the power 1. So which terms will be which terms will have coefficient lambda to the power 1? If you multiply h naught by psi n1, right? If you multiply h naught by lambda times psi n1, then this term will have lambda to the power 1, right? So we can multiply h naught by psi n1. So I have written down over here h naught into psi n1, right? Then what other term can we have? h1 multiplied to psi n naught. This will also have lambda to the power 1 as a term, right? h1 into psi n naught. So over here we have h1 into psi n naught, right? Okay. Then we come on to the right hand side. In right hand side, which terms can have lambda to the power 1 as the value? en naught, and if you multiply en naught and psi n1, lambda into psi n1, then this term will have coefficient as lambda to the power 1. So en naught into psi n1. So en naught into psi n1 and plus lambda times en1 into psi n naught, right? So en1 into psi n naught. So these, now we can equate both these terms, right? Now you must be wondering, if we try and equate such, so this is basically equal to lambda to the power 1, right? This term equates to lambda to the power 1, and over here if you see, we have en to the power 1. So what is this en to the power 1? This is called the first order perturbation, right? First order perturbation, right? Similarly, if you have en to the power 2, that is second order perturbation. Then en to the power 3, that is third order perturbation. So basically, the more the perturbations we have, the more precise our value towards the actual energy will be, right? We are trying to approximate the energy of the system, right? So the more close, the more perturbation terms that we find out for the energy, the more close we get to the exact energy, right? But what happens is that you know, as soon as we go to higher order energies, the difference becomes very less. So we only try and approximate till maximum till second order, right? We don't go beyond that, right? So from this equation we can get the energy of the first order term. But how are we going to get it? And one more important thing that I would like to tell you is that Taylor series is convergent and divergent, right? So in case of a convergent series, what happens is, if we go to a higher order energy term, if we go to a higher order energy perturbation, like if we go to fifth order or sixth order, then we'll get a better energy, right? But it is not always the case. Some Taylor series are divergent, okay? Or you can say there's a particular term, I'm forgetting that term, it's called mtotic, right? Mtotic or something like that, which states that if I plot a graph over here for you, right? So there are some functions or some series which are divergent in nature. Like for example, for smaller energy terms, they will be very close to each other, right? For smaller energy terms, they will be very close. So let's say if I talk about a graph like this, right? So for smaller energy terms, they are very close. And then for higher energy terms, the gap increases, right? So you can have such kind of series as well. So for such kind of series, you have to be very careful. Those are divergent series where the smaller perturbation terms will give you a very precise energy, but larger perturbation terms will give you a very wild energy, which will not be close to the original energy, right? So you have to be careful about these things as well, right? So it's always beneficial to calculate the perturbation for smaller energy terms only, right? So over here we'll try and approximate the energy of the first order perturbation, right? How will we find the energy of the first order perturbation? And most of the questions in the exam are related to this particular first order perturbation only, the energy for the first order perturbation, right? So now let us try and find out that. Okay, all right. So what we do is, this term we got, right? This is what we had got, that h naught psi n1, when we equated the coefficients with lambda to the power 1 as the common coefficient, we got h naught psi n1 plus h1 psi n naught is equal to en naught psi n1 plus en1 psi n naught, right? If you keep on writing with me, if you pause this video and write it with me, it will be much more beneficial and you'll understand in a much better way, right? So now what you need to do is, we have to find out basically the energy of the first order perturbation. We need to find the value of En to the power 1, right? So if you need to find the value of En to the power 1, what we need to do? We have to multiply it with something, right? And all of you know this is a very basic rule of quantum mechanics, that if you multiply psi and the wave function by its complex conjugate, and if the wave function is normalized, the value that you're going to get is equal to 1. So since we need to find out the energy of the first order perturbation, or this term, what we need to do is we need to multiply by its complex conjugate. So complex conjugate of psi n naught is psi n naught star, right? So we are going to multiply and integrate, right? So what we do is, we multiply the whole equation by psi n naught star. So if you multiply the whole equation by psi n naught star, what do we get? Psi n naught star h naught psi n1 plus psi n. So basically I'm multiplying this whole term by psi naught star, right? Psi n naught complex. So psi n naught star h naught psi n1 plus psi n naught star h1 psi n naught is equal to, I multiply this psi n naught star En psi n1, right, plus again psi n naught star En psi n naught, right? This is what we get. Now energy is a constant value, so what we can do, we can take this energy En1 outside. So if we take this energy outside En1, then psi n naught star into psi n naught is equal to 1, right? So we get En1 as the value over here, right? Now what we need to do is, now I'll write it down over here. Wait, let me just check the battery of the phone. Okay, so it is there, right? Right, so what we are going to do now is, we are going to solve this, right? So what do we get finally? We get psi n naught star h naught psi n1, right? So this value you understand, right? En1 is constant, we take this outside, so we are left with psi n naught complex into psi n naught, right, which is equal to 1. So this term is basically equal to En1. This term will basically come out to be equal to En1. So here we have En1, or the first order perturbation value, right? And now what we need to do is, if you see this term and this term, right, this is basically, we have to make use of Hermitian property of a Hermitian operator. So obviously these are quantum mechanical operators, so they are Hermitian. Now what we need to do is, if you see over here, we have this term psi n naught star and h naught. So if you try and write it down, if this is a Hermitian operator and you make use of Hermitian operator, what you can write down this term as, you can write down this term as psi n1 star h naught, Hamiltonian operator h naught, right, into psi n naught whole star. This is the property of Hermitian operator. If you are not aware of that, you can watch any of my videos on Hermitian operator. This is a very basic property of Hermitian operator, that you can write this Hermitian operator in this format, right? So now if you see this h naught into psi n naught, this is very familiar, right? This is very familiar. What is this equal to? This is equal to En naught, right? This is equal to En naught psi n naught, right? This is equal to En naught psi n naught, right? This is basically your h psi is equal to E psi. So this h naught psi n naught is equal to En naught psi n naught, right? And over here also we have En naught, sorry, I've just forgot to mention this, right? Okay, so now what we do, so we basically write this term as psi n1 whole star En naught psi n naught, right? Then star. So if we take the complex of psi n1 star, this will become psi n1, right? This will become psi n1, right, if you take the complex conjugate. And now this is the eigenvalue, and eigenvalue for a Hermitian operator is a real value, and real value does not have a complex, right? It will be basically the same value itself. So this value will remain the same, right, because it's a real value. So real value will not have a complex conjugate, so this will remain as it is, E n naught, right? And this will again turn to psi n naught star, psi n naught star, right? And we have integral, obviously, right? We have integral, obviously. Now if you see this term psi n1 E n naught psi n naught star, and if you see this term psi n naught star psi n1 E n naught, these are basically the same terms, right? These two are the same terms. This term and this term are same, all right? This term and this term are same, and they are on the opposite signs, right? Basically these are equated. So if I take it on the left hand side, this will become minus of this. So basically what is going to happen is this term over here and this term over here will cancel out using the Hermitian operator property, right? Okay, it's about, the battery is about to die. I'll try and film as much as possible, right, because I don't want to make any edits, right? I am planning to make a video which I can just upload right like that. I don't want to do any editing, right? Anyway, so this is what we get. So these two terms get cancelled out. So what will we be left with? Basically your first order perturbation is equal to, your first order perturbation is basically going to be equal to psi n naught star, the perturbed term, the perturbed Hamiltonian, into psi n naught. Now this is very, very convenient. This is very, very convenient. Why? Because the first order perturbation is nothing but the wave function of the system for which you have the exact solution, and basically the perturbed term, the perturbed Hamiltonian. That's it. So you need the perturbed. Hey guys, so unfortunately the battery went out and I had to edit this video. So anyway, so what happens is, like I was stating, that we had reached this point where the perturbation, the first order perturbation, right, the first order perturbation term of energy was equal to psi n naught, the perturbation Hamiltonian, or the perturbed term, into the wave function, right? So which is this wave function? This wave function is of the unperturbed system, right? So for this, it is the wave function for the system for which we already have the exact solution. So it is very, very convenient for us to find out the solution, right? Now before I come on to the examples, there's one more thing that I wanted to discuss. That was that this particular derivation that we have done, this is only applicable to non-degenerate states, right? It is not applicable to degenerate states. Why am I stating that? Because when we use the Taylor series, right, when we utilize the Taylor series, what happened was that psi n naught we had written, psi n, wave function psi n is equal to psi n naught, right, plus lambda times psi n1, like that we had written, right? So if I am assuming, and so on and so forth, right, lambda square, lambda cube, and so on and so forth. So if I, for example, if I take the lambda parameter to be equal to 0, if I take the lambda parameter to be equal to 0, then what will happen is all the terms which had lambda as a coefficient will become equal to 0. So finally what will happen that lambda n will become equal to wave function n, psi n will become equal to psi n naught, right? So that means that there is only one particular wave function for the system. But what if the system is degenerate? Then it will have more than one wave function, right? But according to the assumption that we are taking of the Taylor series, that psi n is equal to psi n naught plus lambda times psi n1, and if we take lambda equal to 0, then we get only one wave function. But for degenerate states, we can have more than one wave function. So this is not applicable to degenerate states, right? Now let us take some example, and to gain confidence, or to improve your confidence, I have taken one example from a physics based question as well. So do not worry, we'll take one particular topic, one example from chemistry based and one example from physics based entrance exams, right? So this was asked in your GATE exam, this physics question, and this was asked in your CSIR net exam, and it's very, very simple. The only thing you need to work on is your integration skills, right? How you can integrate well. If you can integrate well, I don't think there's any question from CSIR net which you won't be able to solve, all right, or GATE examination, or any entrance examination for that matter, right? So that if the lambda parameter is included, then in the perturbation term, the lambda factor will also come into the picture, right? So just keep this in mind, that if we include the lambda parameter, like lambda times first energy perturbation, then the Hamiltonian, the perturbed Hamiltonian will have the lambda term as well in it. All right. So this is the question that we have, that a particle in a 1D box is given to us, and this is a feature that was given in the question, that the potential V between 0 to L by 2. So in a particle in a box, generally the default distance is L from 0 to L, yeah, or from 0 to A, right? So for a particle in 1D box, it is given that the box is perturbed with the potential with the potential, generally a particle in a 1D box, the potential inside the box is 0, but it is given that it's a perturbed system. That means there is some kind of displacement, or there is some kind of deviation from the normal behavior, and the perturbation is such that the potential V0 is there between value 0 to L by 2. So there's some kind of perturbation which is equal to V0 between 0 and L by 2. So we need to find the first order perturbation for the ground state, right? So in the question it was asked the first order perturbation for the ground state. Now what you need to do is, obviously you know that for the perturbation is given to us, that the perturbation is between 0 to L by 2, and the perturbation value is given to us as V0. So for that, what we need to do, and the system is given to us as a particle in 1D box. So for a particle in 1D box, we have the exact solution, right? The energy is equal to n square h square by 8ml square, and it is given to us that we need to find the energy in the ground state, right? So it can be given to us to find the energy of the perturbed system, or the energy of the first order correction in the energy, or it could also be asked the total energy of the perturbed system. So depending on that, you have to answer. If the first order perturbation energy is asked, then you simply calculate that. If the total energy of the perturbed system is asked, then you add both the energies, right? So particle for a particle in 1D box, the energy is n square h square by 8ml square. So for ground state, we will take n equal to 1, so it will become h square by 8ml square. So now we'll find the first order perturbation energy, right? So what we have to do is, we have to use this formula. So what is a wave function for a particle in 1D box? The wave function is under root 2 by L sine n pi x, right? Under root 2 by L sine n pi x by L. This is the wave function. I hope all of you know the wave function for a particle in 1D box. These are small things that you need to remember. The wave function for a harmonic oscillator, and the wave function for a hydrogen atom, because these all are basically these all have exact solutions. So using these only, we will try and find out the perturbation. So these wave functions you should remember. So what I have done to find out the perturbation, under root 2 by L sine n pi x by L, and the perturbation is V0. So I have written the perturbed term, which is equal to V0, right? The Hamiltonian for the perturbed term, that is equal to V0 into again under root 2 by L sine n pi x by L, and the range is from 0 to L by 2, right? Now what we do, V0 is a constant value, potential is constant, so we can take V0 outside, and under root 2 by L into under root 2 by L will become equal to 2 by L, and 2 by L is also a constant value, right? Length is constant and 2 is obviously a constant number. So I have taken 2 V0 by L outside, right? V0 and 2 by L I have taken outside, so we have 2 V0 by L over here. Now what I have done, now I have to basically integrate sine square n pi x by L. So for integrating sine square n pi x by, if I integrate sine square n pi x by L, this is what you need to do. You need to know how to integrate, right? So if you integrate sine square n pi x by L, what will you get? So 2 V0 by L is constant, you will get minus 1 upon 2 n pi by L, minus 1 upon 2 n pi by L sine pi x by L cos pi x by L plus x by 2. This is the, when I do the integration of sine square n pi x by L, this is what I get, right? And the term is from L by 2 to 0. So now what I have to do, I have to simply replace the value of L by 2. So if I replace the value of L by 2 over here, sine pi L by 2, right? So L and L will cancel out, so this will become sine pi by 2. Sine pi by 2 is equal to 1. But if you see over here, this will become cos pi L by 2. So cos pi L by 2 upon L, this will become equal to cos pi by 2, and cos pi by 2 is equal to 0. So this whole term will become equal to 0. So we don't need to calculate. So this whole term will become equal to 0. And then over here, if you replace x by L by 2, this will become L by 4, right? So this has become L by 4. So we have L by 4, right? And now what we are doing? Now we are taking 0. So if I take 0 over here, sine 0 is 0, so this whole term will become 0, this whole term will become 0, and this is also x, so this will also become 0. So we are left with L by 4. So if I multiply 2 V0 by L into L by 4, what do I get? So 2 V0, so LL cancels out, and this cancels out. So basically what I get is equal to V0 by 2. What I get is equal to V0 by 2. right? So this is the first energy correction, or the first order energy correction for the particle in the 1D box, or for the system that is given to us from 0 to L by 2. The energy correction is V naught by 2. So if you take this V naught by 2 as the energy correction, so what will be the perturbed energy? The perturbed energy will be n square h square for a particle in a 1D box for the ground state. The energy, the perturbed energy, the total energy for the perturbed system will be h square upon 8 ml square plus V naught by 2. So that was your answer. Okay, as simple as that. Simply take whatever the perturbation is given to us and apply it in the wave function of the non-perturbed system or unperturbed system, right? And then just integrate and you'll get the answer, right? Let us take the second example. So the second example we have, again, only the integration part is a little tough. That if you master or if you practice, then this thing is very easy. And in fact, in CSI Net exam, a lot of integration is not asked, right? They are very direct questions, so that can be easily solved. But for gate exam, sometimes you need to do some kind of integration. But again, if you understand the concept well, there's nothing that you need to do, right? There's certain things that I would tell you, some tricks, like for simple harmonic oscillator, if it's an odd function or if it's an even function, there are particular values that you will definitely get, right? So these kind of questions were also asked. But anyway, right now I'm just trying to help you out with the perturbation term, right? So then there was this another question in gate physics exam where it was given that the perturbation in a particle in 1D box, okay, is equal to W, okay, is equal to W, where W is equal to beta into X, right? So it was given that the perturbation of a particle in 1D box was given to be beta X. The perturbation term for a particle in 1D box was given to be W, where W was equal to beta into X, where beta was basically a constant value. So it was given to us that beta is constant and the perturbation is equal to W, and W was given as beta into X. So what did the question ask? The question asked to find the perturbation, the first order correction in the perturbation, or the first order correction in the energy term for that particular system that is perturbed. So we had to basically find the first order correction only, right? So the formula for a particle, again we use the same thing, the wave function for a particle in 1D box, which is equal to root 2a upon sine n pi x by a. You can either use L or you can either use A. Depending on the question, you have to take L or A. Sometimes in the question they take it as L to 0, sometimes in the question they take as A to 0. So this becomes sine n pi x by a, right? Then into beta x, which is the perturbed term. You can write down over here W, or I've just written down beta x, right? Into root 2 by a sine n pi x by a. So again we have to find the perturbed term for ground state. So n I can take equal to 1, n value I can take equal to 1. Now beta is a constant, so beta I can take outside, and this 2 upon a is also constant, so this becomes 2 beta by a, which I take on the outside. So again I am left with sine square n pi x by a, but now I have one more term. In the previous question I had only sine square n pi x by a, but over here I have one more term, which is x, because in the perturbed term x is a variable, so I have to consider this x as well. So this is sine square n pi x by a into x, right? Now if I solve this integral, so if I take this 2 inside, this becomes 2 sine square theta, and all of you know a very simple trigonometric formula, 1 minus cos 2 theta. 2 sine square theta is equal to 1 minus cos 2 theta. So using that formula, I take the 2 inside, so I'm left with beta upon a, and then I integrate that value, 1 minus cos 2 theta into x. If I integrate that, I come up with this whole term, right? X square upon 2 minus xa upon 2 pi sine 2 pi x by a minus a upon 2 pi whole square cos 2 pi x by a. This is the whole term that I get, right? So again, like I told you previously also, your integration should be good. Now what I need to do, now simply I have to replace the value. If I replace this a is the upper limit, so I replace the a value over here, so this will become a square by 2, right? This will become a square by 2, and this is sine 2 pi x by a. So if I replace this x by a, this will become sine 2 pi, and sine 2 pi is equal to 0, so this whole term will become equal to 0, right? This whole term will become equal to 0. So I'm left with a square upon 2, right? I'm left with a square upon 2, and then over here what will happen, the value is already a over here, so this will become a square upon 4 pi, and if I replace over here a, so this becomes cos 2 pi a upon a, so this will become cos 2 pi, and cos 2 pi is equal to 1, so this will become minus a square upon 4 pi square, right? then minus of, now I have to take 0 as the lower limit, so minus of 0, so this will become 0, then sine 0 is also 0, so this whole term will also become 0, and cos 0 is equal to 1, so this term will be as it is, so minus of minus a square upon 4 pi square, right? And if I solve this, so a minus a square, this will become plus, so this and this will cancel out, so I'll be left with beta by a into a square by 2, right? So if I solve this, a and a cancel out, so I'm left with alpha beta or a beta, whatever you like to call it, alpha beta or a beta upon 2. So this is the first order correction in the energy for a particle in 1D box for which the perturbation was given to us as beta x. So the answer is a beta by 2. As simple as that. A very simple 2 marker from your GATE physics examination. So as you can see, there is nothing tough. Once you understand the concept, it's very easy to solve any question. All you need to pay attention is sometimes in the question the integration term could be a little complicated, so you need to work on your integration skills. That's it. The whole procedure or the whole system or the whole concept of perturbation theory, as you can see, is very simple. All right, so anyway, I hope you found this video useful. I have actually put in a lot of effort to make this video. It did not come out as I had expected. I mean, I could have made a much better video, but like, I tried my best, right? I am short of time, so I could not give my 100%, but yes, I did put in a lot of effort, right? As much as I could possibly do. So anyway, I hope you found this video really useful, and in case you did, do not forget to subscribe to this channel. And that's it. Thank you so much, and do give it a big thumbs up, right? I did actually put in a lot of effort, right? So thank you so much, and I'll see you in the next video with some more, maybe variation theorem or second order perturbation, some questions related to that, right? Thank you so much for watching.